This is a lesson on how to incorporate Newton's third law into more complex systems of objects with 2D forces. And I'm going to remind you for Newton's third law of motion, this is a force between two objects in contact with one another. So if there's a force on one object, there must be a force from the other object onto the first object. It's equal and opposite. And so when you draw free body diagrams, remember to include those Newton third law pairs in your free body diagrams. They won't be in the larger system, but you have to include them on the smaller ones. So when you draw free body diagrams, keep track of your Newton's third law pairs. And then when you're writing Newton's second law's equations, you'll have multiple objects on which to write those equations, and you can have multiple unknowns going on as well. To exemplify this, I first picked a one-dimensional problem with 3 books stacked on top of each other, atop a rough table. So there's a lot of things going on here, and I'm going to just draw a general rough sketch to begin with. And I have 3 books, so let's get 3 books. 1, 2, 3, and they're all 2 kilograms, so I hope they all, and I'm going to call this mass bottom, mass middle, and mass top, so we can tell them all apart, but they're all the same. M1, M2, and M3 is 2 kilograms. It says that there's a rough table, so I'm going to note, and I do this by shading the surface, that there is some sort of mu that's not equal to 0, and they give us, let's see, the coefficient of static friction and the coefficient of kinetic friction. So I can write those down. Mu s equals 0.38, and mu k is smaller, as I expected, 0.26. Okay, so we have a general sketch of the situation, and we're seeing different books stacked on top of each other, and so they'll be exerting forces against one another. It says an external force is applied to the bottom book, which accelerates the entire stack of books. What is the minimum external force such that the top block doesn't slip on the stack? Okay, the coefficient of static friction between the books is 0.38. Okay, so that's between the books at these surfaces. And the coefficient of kinetic friction between the bottom book and the surface is 0.26. So that goes here. So we're seeing that there's different surfaces in contact with one another. And what isn't clear in this problem here, and it will be in other problems if there's a picture or it'll be stated, is that this force here that's being applied is completely horizontal. We're just going to keep that easy. And so when I look at the system of blocks, there's a force on the system of blocks, and there's also a force of friction from the surface underneath. Okay. What is the minimum external force such that the top block doesn't slip on the stack? So it seems like we have to focus on the top block. It says it doesn't want the top block to slip, so let's maybe draw a free body diagram of that top block. Here's the mass of the top. Of course, there's going to be a normal force, and I'll call that NT, and the weight is WT for top. And this blue force I drew here, it's a contact force, and it's being applied to the bottom, right? The external force is applied to the bottom book, not the top book. So what force is causing the top block to move? Well, in this situation, and I had noted this when I talked about friction in previous lectures, is sometimes friction causes acceleration, and it may creep you out. But when I look at this situation, let's draw acceleration in here. There's acceleration. It's accelerating in this direction. So the top block must be accelerating in this direction. And the only force, the only other object touching the top block is the middle block, and the middle block and the top block have friction between them. So it must be that the friction force on the top block must be causing this acceleration. Again, the friction is causing the acceleration. That's the true fact here. And it may seem creepy, but this is how our shoes work as well. So when I look at the top block, and I'm just kind of following my nose here, I can write out a Newton's second law equation. The sum of forces on the top block has to equal the mass of the top block times the acceleration. Well, the force on the top block is the friction force between the middle block and the top block. So I'm going to put the force of friction here, and you can put top from the middle has to equal mass top times A. Well, let's write out what we know for the friction force. The friction force has to be the normal force times the coefficient of static friction. And I'm going to note that this is static friction because what is the minimum external force such that the top block doesn't slip? We do not want slipping between the middle block and the top block, which means that they're in a static situation, and therefore we need to put static friction into this equation. And so we're looking at a maximum static frictional force and a minimum acceleration. Remember, the force of friction static is less than or equal to mu s times the normal force. And in this situation, we're going to let it be the maximum value so that we can have an equal sign in here. It then becomes an equal sign. The normal force in the y direction, we can do a force analysis in the y direction. The sum of forces in the y direction has to equal mass top times A in the y direction. And what we're going to find out here is that the normal force upward counterbalances the weight downward, and that the normal force on the top block is the mass of the top block times G. And I'm going to put that down here, right? This would be the normal for the top block. Has to equal mass times A. So let me plug that in there. Mu S times mass of the top block times G has to equal mass of the top block times A. Beautiful things happen. I love when mass cancels. You could have plugged it in, but you end up canceling. It ends up canceling itself out. And we can find this minimum acceleration. The minimum acceleration equals the mu S times G. Well, I know both those values, 0.38. G is the acceleration due to gravity on the planet Earth, which is 9.8. And when you run this through your calculator, you get the minimum acceleration to be 3.724 meters per second squared. Okay, that's all that is. What is the minimum external force? Okay, so I found the minimum acceleration, and I need to go back and ask, what is this? Must this force be then? Well, the force is being applied to the bottom block, and what I can do then is kind of think about what makes sense to me is to do this whole system. If I look at a free body diagram of the whole system, and I'm going to say top plus middle plus bottom, we're putting them all together, it will have a normal force, and I'm going to call this normal for the total system as opposed to just the top block. This is all of it. This will be the total weight. The blue force is still being applied, so we have F. It's being applied to the bottom block, but when I draw the whole system, it doesn't matter where I draw it on there. And the last thing I need to put on here, remember that there's friction down here with this surface, so that there's some sort of resistive force of friction, which is kinetic down here, force of friction kinetic, because the bottom block is moving relative to the surface that it's on, and it will oppose that motion. I'm going to note that the acceleration in this situation is still to the right. And I'm going to assign a coordinate system here. I didn't on the other one, except that I did kind of inherently, I did this, y and x. So make sure you're assigning your coordinate system explicitly. Let's see. I have a frictional force, and I know I'm going to need the normal force. When I look in this situation, the normal force and the weight oppose each other. Normal force minus the weight. It's not always like this, and when I introduce friction, I gave many examples where the normal force is not the weight. In this situation, it is. So we can say that this is M total times G. Let's do Newton's second law in the x direction on the total. All right, M total times A. This is all of it. I'm going to have F in the positive direction minus the force of friction, kinetic. So that'll be mu K times the normal force has to equal M total A. We're trying to solve for F, so I'm going to move this term over to the other side. F equals M total times A plus mu K times the normal force, which I know is M total times G. You can factor an M total out here, and you get A plus mu K times G. And just to make this look nice with numbers in it so you can see what the numbers look like, the total mass is 6. The acceleration I already solved for, 3.724. Mu K is 0.26, and 9.8 is the same 9.8 that we know and love. When you solve this, when you plug this through your calculator, you get 37.632 newtons. And that is the maximum force that can be applied here, right? The maximum force that can be applied there before the top block starts slipping. If you push harder than that, the top block is going to fall off the top, and that static friction is going to be overcome at the top. But we had to take into account the kinetic friction at the bottom with the bottom block because the force was being applied to the bottom block. Let's do another complicated example, just so that you're practicing and get some experience looking at problems that are a little bit more complicated. This problem says two adjacent boxes, and there are two masses, are being pushed up a 25-degree frictionless incline. Okay, I like frictionless. We don't have to deal with friction. By a 445 Newton force oriented parallel to the ground, not the incline. Okay, so when I look at this, let's draw a quick sketch over here of what's going on. Here's the 25-degree incline. I can draw that in here. Here's 25 degrees. There's two blocks, two adjacent blocks, and I am not told the order, but since the 45 is first, I'm going to put it there. So there's the 45 and there's the 21. The force is being exerted on the larger box. There it is. The force is being applied on the larger box, and the smaller box is being pushed by the larger. So when I put this 445 Newton force in here, and I'm going to just draw it as a blue, right? F equals 445 newtons. It says it's being oriented horizontal, parallel to the ground. Not parallel to the incline, but parallel to the ground. So I'll go like this, okay? You can kind of get the feeling maybe that the blocks will accelerate parallel to the incline only. And that means that a coordinate system would have to be oriented parallel to the surface of the incline along with the acceleration. So there would be a coordinate system. And what I'm going to note is this force being applied then must be decomposed into a component horizontal to the surface and a component into the surface. And I'll call this Fy and this Fx. So we're going to have y motion, and we're going to have to do some analysis in the y direction and in the x direction separately because this force gets divided up. It says calculate the acceleration of the boxes as they move up the incline. So I already am anticipating the acceleration. And the force the larger box exerts on the smaller box. So that's an internal force in here. They want us to find that internal force in there. So in order to find the acceleration of the whole system, I'm going to consider the whole system. I'm not going to worry about those individual blocks on their own. I'm going to do a free body diagram of the whole system. So I'm going to do that over here. Let's do A over here. Here's the two boxes. And you can draw your free body diagram this way or this way. I don't mind either way. I'm actually going to do this direction to get some practice doing that. When I look at both of them together, so I'm going to have 45 plus 21 here, there's going to be a normal force away from the incline. Of course, there's a supportive incline, and I'm going to call that N total, the normal force for the total. The two are together, so they're going to have a weight together, a total weight, and it's oriented at a 25-degree angle. Right? When I draw it on this diagram, it goes straight down. And notice that this angle here is the same as the 25-degree angle here. This angle and this angle are both 25 degrees. So then when I draw that in here, here's the 25-degree angle. I'll draw it like this. So the weight needs to get decomposed into a y component and an x component, and there's the angle 25 degrees. I'll call this wx, and there's the total weight. I still need to take into account the force. The force is being applied at an angle. Notice it's parallel to the ground here, but it will be at an angle on here, and here's the fx and the fy. Fx, fy. Again, we're going to note that here's the 25-degree angle here, and we can see it over in this diagram here. Is that all the forces? Yes, that is all the forces. There's a lot of things going on. One last vector I'm going to draw in here is the acceleration vector, which is parallel to the incline. And I'm just going to remind us that the x direction is positive that way and y is positive that way. So that when I do an equation in the x direction, let's do Newton's second law in the x direction. I'm going to put it up here because I anticipate some algebra. The net force on the total system has to equal mass of the total system times A, which we're trying to solve for, on the total system in the x direction. Remember, this is in the x direction, so let's just isolate the x direction. When I look at the x direction, I'm going to have the x component of the 445 newtons is in the x direction, and then the x component of the weight is pulling back down the incline, so I'm going to say minus the x component of the weight. That'll equal m total times A. And we can think about this. When I think about fx and fy, fx will equal 445 cosine 25, and fy equals 445 sine 25. So those are both values I can use in an equation. So fx is 445 cos 25. And I'm going to solve for acceleration first here. Acceleration equals f cosine theta minus the weight component. Well, when I look at the weight, and you can see it either in this picture or in that picture, the x component of the weight is the sine. Remember, see, it's the opposite over 25. It's the opposite leg from the 25. So when I write out wx and wy, and I can do that down here, wx equals m total times g sine theta, and wy equals m total times g cosine theta. Okay, watch out for that, sine theta. So then when I bring it up here, I will have m total times g sine theta for the x component. And then I can divide, because I'm solving for acceleration, I'll divide by m total. And we can do this. F cosine theta, so I have 445 cosine 25 minus m total. Well, 45 and 21 is 66. So I have 66 times 9.8 sine 25, and then I will divide by 66. And that will give me the acceleration of the system. The acceleration of the system is then, when you plug this through your calculator, 1.9691 meters per second. And just to review a little bit while I'm solving this problem, right? And you may recognize that I have some familiarity with solving these types of problems and how to set it up, how to stay organized. You may be more wandery around your page, and that's perfectly fine. I'm okay with that. The highlights here that we want to keep in mind is draw your free body diagram. If we're looking for an acceleration of all of the system and we know the force being applied to the system, we can calculate the acceleration of the system by using a free body diagram of the entire system. Again, I chose 2D. This is 2D. We have more complicated forces going on, so decomposing the forces is the challenge of this problem. Can you get the right numbers in the right places to do the calculation to get this number for the acceleration? On exams, of course, I will be giving partial credit for if you set up the equation correctly. So any of the work that you put all the way up here, all of that work is important and you will earn partial credit for it. Your free body diagram, you will earn partial credit for it. If you don't get the right answer, you will still need to draw the free body diagram and show me how you decompose forces, what you labeled where, and how that contributed to writing out your Newton's second law equation. Because remember, that's how we get second law equation, is from the free body diagram. We draw the forces on there, we can see the forces in the x direction and put that equation together. Okay. Now that we have the acceleration, we solve part A. It says, what is the force the larger box exerts on the smaller? Well, when I think about these boxes, in order to get that internal force, I'm going to separate them out. And I could do a free body diagram of the 45 kilogram mass, or I could do a free body diagram of the 21 kilogram mass. You will learn, physicists think, as easy as possible, and there are the least amount of forces on the 21 kilogram block. Let's draw a free body diagram of that 21 kilogram block. There it is. There's a normal force. Of course, there's a normal force. There's a weight. The 21 kilogram block is still on the incline, so its weight force will also be at an angle. So I'll call this W21. Note that it has, again, a Y component and an X component for this block. The only other force on this block is going to be the force from the other block on it, on 21 from 45. It's the one causing it to accelerate up the incline, right? So it's accelerating up the incline. I can assign a coordinate system, just like the other blocks, X and Y. There's the other ones. And so I can write out the Newton's second law equation for this pretty easy from what I know from the other blocks, M21 times A. So when I look on this side of the equation, F, the one force from the larger block on the smaller block, is there. And then I also have to take into account the X component of the weight on this 21 kilogram block. That will equal its mass times acceleration. Okay, so I'm trying to solve for this, an expression for the X component of the weight. Well, I know that from earlier, it'll be the same form as the X component for all of the blocks. Mass times gravity times sine theta. So when I solve algebraically, the force on the smaller block from the bigger block will equal 21 times the acceleration, 1.961, minus 21 times 9.8 times, again, the X component is the opposite leg from the angle, and so we're going to put sine 25 degrees here. You can run this through your calculator, and when you do that, you get, oh, there's a plus sign here, sorry. When you move it over, there's a plus sign. It should add together. 21 times the acceleration plus 21 times g times sine 25. When you add those together, you get 128.3249 newtons. Seems reasonable. I would say it has to be less than 445, right? If 445 is pushing here against the whole thing and only a component actually translates to acceleration, and then this block is smaller than the other ones, it's going to be smaller than the 445. So there is the answer for that problem.